Good afternoon, everybody, and welcome back to this Altecnic CPD in partnership with CIBSE West Midlands. Just a few housekeeping rules before we make a start, if I may. So first of all, welcome and thank you for joining the Altecnic CPD today, delivered in partnership with CIBSE West Midlands. The CIBSE West Midlands region aims to expand the knowledge of its members through various learning initiatives, and we hope you find today's topics insightful. Just as a bit of courtesy to myself and the other participants, we politely ask that all delegates put themselves onto mute when not talking, and know that anything written in the chat is visible to all on the call. It is an open forum. There will be time for a Q&A session at the end of the CPD, so please write any questions that you have into the chat or use your raise hand function, and I'll get back to you as quick as I can. There's a colleague with me who is monitoring the chat, so we'll pick those up as quickly as we can. Also, following on from the CPD, you will also receive your CPD certificate for the attendance of this course. So we'll make a start. So today we're going to take a look at sort of central plant versus design and sizing with HIUs, and a little bit about the district heating side of things and what sits in the heat networks. So course objectives and what we hope you're going to learn at the end of the day will be things like typical network issues. You know, how can we overcome them? Well, first of all, what are they? How can we overcome them? Working with primary flow temperatures, whether they be high, low, medium temperatures, you know, have a look how it can impact on the performance of the HIUs and what that gives out to the dwelling. The keep warm functions, what that means to a system, what it means to the network as well. I think it's important that we understand the relationship between the two. But also, how can HIUs assist or hinder efficiency? And that might sound a bit of an open-ended question, but you know, as much as there's assistance to us, or if they're not done correctly, it can hinder the efficiency of their network. So we'll take a look at those as we go through the presentation. So first of all, typical network issues, something that we regularly see or regularly hear about with issues within the network. There's a multitude of different things, starting from the top there. So oversizing, so whether that be oversizing of plant, oversizing of pipe work, oversizing of HIUs, you know, all of this becomes an issue when it comes to the efficiency of the network. High speed pumps with minimum turndowns, so pumps run at constant speed, you know, not necessarily being controlled by inverters, so variable speed and working to demand. They're just running at the full system speeds. Low system delta T's, you know, we're looking for those nice low return temperatures, looking for a wide delta. If we are getting that low system delta T or a high return temperatures, obviously something's not right with the system or with the network, so we have to look what those are. Overheating of corridors, I'll explain a little bit about more as we go through to the presentation, but essentially when we turn pipe work into radiators in communal spaces and corridors, it just adds to the inefficiency in network and it's wasting energy and in turn wasting money. High network losses kind of comes hand in hand with heating of corridors. If those network losses, if it's coming from pipe work and pipe works are acting or is acting as a radiator, say those network losses or the high temperature losses are an issue. Lack of or fluctuating domestic hot water temperatures, key thing, something that we hear a lot of from end users when they come through to our technical line is that, you know, we're having issues with hot water, whether it be delivering no hot water or lack of hot water or low temperatures. That's always a big issue. Long response times, not necessarily unique to district heating or to heat networks or to HIUs. But what we mean by long response times is when you initially turn that hot water tap on, the amount of time that you have to wait for that hot water to be delivered to your outlet. So, you know, how can we look at reducing those? Low space heating delta T's, again, so if we're not balancing the space heating properly, the radiant circuit properly, we're still affecting the delta T's, which in turn is going to have an issue or a knock-on effect onto the heat network. But also things like space heating starts, you know, when the initial heating comes on, what impact does that have on the system? You know, what issues does that cause? But that's something that we'll look at as we go through the presentation. So those are sort of some of the things that we identify as typical network issues within a district heating environment or a heat network. So first of all, if we start where we should, and that's with the apartment, you know, sizing does start with the apartment, not in the plant room. I come from an install background from 20 years plus where we would put the biggest heat generator we could into a plant room. We would produce as much heat as we could, and then we'll just work out how we're going to use it after that. It's not really the way we work anymore. You know, the sizing starts in the apartment. We work out the load, exactly what we need, multiply that by the amount of pumps we need. Then that will give us the size of what we're going to start putting in the plant room. Overestimating domestic hot water loads is the start of the problem. We seem to think that we need these huge amounts of domestic hot water loads for the systems to work properly, and we do. You know, domestic hot water uses a hell of a lot of energy when it's coming through the heat network. But we've got to size that correctly. We've got to make sure the loads that we put in there are right. And CIBSE CP1 that offers some kind of guidance as to where we are with apartment loads. So we can see there, you've got studios at 1 bed flats, 1 bed, 2 beds, 2, 3 beds, and bigger than that. So you can see the typical demand or the expected demand that should be available. This is available from CP1. Should you want to take up any of the information from there, it's always a good reference guide and also a good course to do if you want to get a qualification for something like that. But it gives you an insight into exactly where we're looking at. So, from kilowatt ratings, so what, a 1 bed studio or 1 bed flat is 25 to 30 kilowatts, while 1 to 2 bed 30 to 35, and then 35 to 45 as we increase in size. So we can see there the increase in kilowatt loading as we increase on the size of the apartment itself. So when we size in, always start at the apartment and the heat demand that's needed, not what we think we're going to need, and then divide that by the flats. Oversizing the HIU, real big issue that we see. Specifications that we've seen for 90, 110, or even 115 kilowatts of domestic hot water demand. It's a phenomenal number. It's something that is far outweighs anything that we need. We often think that a 35 kilowatt combi boiler into family homes, yet we feel it's too low for a HIU. We've only got to look at the comparisons there and see where we are and see the comparisons that can be made to what's already in the market, instead of overestimating and oversizing the HIUs and causing problems down the line, with cost implications, performance implications, all that sort of stuff. We have to be very clever, very sure that we don't implement those extra costs into the system. System size to ensure the abundance of hot water rather than optimal efficiency. Obviously, we don't want people to have starvation of hot water. We want everyone to have as much hot water on demand as they can, but we can work out that. We can, roll that into the optimum efficiency of the network. Just takes a bit of time, just takes a bit of calculation. We just have to make sure we do that at the outset to make sure we're sizing the plant correctly for the HIUs and for the demands that we have. So oversizing the HIU leads to a number of things. So less turbulence in the plate heat exchange, which is less efficiency in heat transfer, or less efficient heat transfer. We want to create turbulent flow in there. We want to keep the water in there as long as we can to get that energy transfer as strong as we can to then give the nice hot water, or the hot water flow at the outlets. Reduce the self-cleaning effect. Now, what we mean by that, if we're slowing the speeds of water down, the shearing effect that we call, which is high velocity traveling through pipework or plant, we start to lose that effect because we're not traveling, the water's not traveling through the system as fast as it should. And an increased unit cost of the HIU. The bigger the HIU, there's obviously going to be a cost implementing on that. I'm going to get my words out. So we have to be very careful that we are, sizing it correctly so the costs all remain where we need to be. So the way we can start to work it out now, when we are working on multiple factors, is what we call a diversity factor, or applying a diversity factor. And the one thing to remember is not all dwellings will have 100% demand 100% of the time. So we must apply a diversity factor. It's also known as a coincidence factor. If you imagine we have a block of 100 apartments, we then apply a diversity factor to that. And all that diversity factor is the number of simultaneous outlets that are going to be open at any one time. There is an equation that we can work out. Again, it's based from some CIBSE CP1 in how we do that. The bigger the apartment, the easier it is to apply a diversified load, because you've sort of got a little bit more room for error. But the smaller the apartments, the more critical it is that those calculations are done correctly. So obviously, say that the more the apartments, the more that diversity factor will be applied. And again, it's a bit small there, the text now, so I do apologise, but all this information is available in some of the guides and stuff that we have available. So if you want some of the guides after that, we can share these during the presentation as well. When we see then the effect or the effect of correct diversity, there's different standards that you can work to. So DS439, F101, BS6700, and also BSEN 806. But we can see there the diversity load, the coincidence factor, divided or alongside a graph with a number of flats. So the more flats we have, the coincidence factor reduces. So it always helps, when bigger the apartments, the easier is to apply that diversity factor. So always really important that we apply the right amount. Sometimes, it can be a 12% diversity factor, 15%. All depends on the building. And we have to remember as well that you have to apply a diversity factor, which is unique to the building site that you've got. The way that buildings work are very different. If it's student accommodation, the loads will be different times. Whether it's a care home, whether it's private residential, social housing, whatever it may be, each building will work in a different way. You have to understand the building load to understand the diversity factor and implement the right factors into the system itself. So oversizing the energy centre, we're focusing a lot on oversizing. It's something that's just very, very prevalent in the market. We're getting very much better at it. There's some very, very good people out there who are pushing for efficiency in the systems, but oversizing can still be an issue. Now, from boiler sizing, you can work out for a number of apartments times your domestic hot water load times your diversity, the number of apartments times your heating load diversified by the domestic hot water of the apartments. So that's how you can size your boiler. Things like thermal store sizing. So the volume should be equivalent to 10 times of the primary water at peak demand as a minimum. Sorry, 10 minutes. So what I mean by that, your thermal store should hold 10 minutes worth of water at your peak diversity load. So if you've applied a 15% diversity factor, you should be able to store 10 minutes of water to deal with that peak demand. Based on the domestic hot water delta T from the HIU, and the volume of the primary network must be included as well in that sizing. So you've got also there's a volume of water which is going to be circulating around the system. That should also be included in the thermal sizing, store sizing as well. Primary pipework size as well. This is really important. This is how we get the water around efficiently. We've got to get the right amount of temperature to the right place at the right time. Again, number of apartments times the heating load in kilowatts divided by 4.2, then times the delta T of the space heating. The number of apartments times domestic hot water load is kilowatt divided by 4.2 times the delta T from the HIU. So it's critical you've got all the information up front when you're sizing it, so you can apply the right systems or the right calculations to it to get the right sizes what you're looking for. So optimization of network pipework. Typically in the UK, we've sized pipework based on 250, 300 pascals per metre. But where do we take this volume from? Now, this dates back to the days of the guidance documents based on constant volume systems. The issue with this is that it's increased velocity, could lead to noise, erosion. However, as we are calculating pipe diameters for a constant speed system, the velocity would occur 24 hours a day, 365 days a year. It's very different in the way we work now. We used to, like it says in here, size a system where we shift a constant volume of water for 365 days of the year, 24 hours a day. We're moving away from that now. Networks are different, and the calculated flow rate may only occur for just a maximum of 10 to 15 minutes per day at peak demand. So we have to look at a way to diversify that load. So therefore, erosion will be massively reduced. As for noise, well, the peak flow rate only occurs at times of high domestic hot water usage, say when the tenant is running a bath. So when we look at the load on the network, when we've got the heating on, the load is a lot smaller because we're moving water at a lower temperature at a slower rate around the system. But when we're looking for hot water, the energy that's used in the system is far greater. The heat transfer is far greater, so we have a bigger peak demand which sits on the system itself. Okay, sorry. There's a couple of questions. I'm just going to go back. Apologies to the ones who have asked the questions. Let me try and pick those up. Okay. Oh, there's a few questions here. Right. So, what diversity factors would you consider for domestic hot water size and consider this for a good idea instead of an HVAC standard? Also, would you consider diversified heating load when sizing network? Okay. So when it comes, we always look at DS 439 because it's such a more stringent standard than what we have in the UK. So the British standards of what we use here are probably not as well tuned as what the DS standards are, the Danish standard. Places like Denmark, Sweden, they've been using heat networks and district heating for a huge amount of time. They're very good in what they do. So we would always base a lot of our calculations on what it states in DS 439, just because it's a very good standard. So also, would you consider diversifying heating load when sizing network? To a degree, the biggest load is always going to come under domestic hot water. You should always apply it to see where we get to, but you're always going to apply a greater demand on the network when you're taking hot water because the demand is so much greater on the HIU. The plates are a lot bigger, the energy transfer is a lot greater, so we have to make sure that we've got a worst case scenario, which will be when we take in domestic hot water from the system. So hopefully that's answered that question. Only specific considerations for retrofits or upgrades to existing central plant when incorporating HIUs and how can potentially challenges be addressed. Retrofit is a massive market now for district heating, and we have to make sure that the system is fit for the use of HIUs, which is really important. You cannot necessarily just adopt the existing system and make sure, again, your pipework sizing is right. You've got to get the velocities right. You've got to get your flow rates right. You've got to get your sizing right and your heat counts right. So Yes, you know, retrofit is great, but it's got to be fit for purpose, and we have to do it right. So if it means stripping out pipework and redoing it, so be it. If it means redesigning the plants, so be it. But you know, there are certain things. The consideration has to be the efficiency of the network. So that's always an important one. Next question: if I'm working from the energy centre supplying to 4 identical blocks of towers, do I need to apply diversity outlets at the secondary pump or at the bottom of it? So your diversity factor has to be applied across the whole network. So because if you've got one central plant feeding 4 blocks, you're still essentially feeding one system, although they can be fed from separate blocks. So your diversity factor will be applied across the whole development because we're looking at the energy efficiency across the whole network per se. So we'd have to take it from all 4 blocks as being one identical system, not each block or each riser itself. What would the primary delta T? What would the primary delta T that you would consider for primary heating and primary domestic hot water? Again, depends on network. You know, the bigger the delta, the better. We would always look for something in the region of between 30 and 40 degrees delta T on a good domestic hot water system. Some of the bigger plate heat exchangers in HIUs will give you far greater deltas than that. Heating depends, you know, we will look at some of the things as we go through the presentation on heating, on how we can increase that delta. It's all about surface area. It's all about, you know, transmission of heat. The better heat networks are ones that transfer the most heat. So if we can draw that out by using like larger surfaces like bigger rads, underfloor heating, utilizing those bigger areas to take the heat off, the more efficient the network will be because we're increasing that delta and we're taking more energy from the system. But as I say, you know, we'll look at those as we go a little bit further into the presentation. So I hope I've covered the questions. I'm going to go back to the presentation. And so my colleague is monitoring it. So if anything else comes up for the presentation, I'll stop and go back again. So hopefully I've covered those ones off. Back to optimization of pipe work. The noise issue, therefore, is not really an issue because we're not going to be flowing the pipe work at that demand. Therefore, we can reduce the size of the lateral pipe work, we can reduce the losses in this pipe, but crucially, we also reduce the volume of water. So this is where now we start to look at the size of the pipe work and how we can really use it as an optimization to the system to make it run a lot better. So with the reduced volume, the laterals can be left to go cool. The volume of the cool water in these short, small diameter laterals can be easily and quickly purged through the HIU, and the response time to the apartment is not adversely affected. Therefore, the lateral pipework values of 500 to 600 pascals per meter or even higher can be encouraged. So to try and put a bit of context around that, you know, essentially what we've always done is put big pipe sizes in, moved water through at a certain velocity or a certain flow rate as we go through, which is great. But the bigger the pipework, the bigger the radiant space we've got for heat loss. If we then start to reduce the size of the pipework, so if we come down from, say, for instance, 2 inch to 1.5 inches, 1.25 inches, or 1 inch, what we're doing is we're increasing the velocity, so we're increasing the flow rate through there. We're reducing the surface space, so it doesn't become such an issue when it comes to heat losses. And the higher the flow rate, then the more energy we can push through there as well. So ensuring that your pipework is sized optimally is key to this, and the flow rates and the pipework size, you know, should work hand in hand. So hopefully that's cleared that one up. It was demonstrated in recent testing carried out in the Swedish Institute or RISE, so it's Technical Institute of RISE, the proportion of mechanical control valves within the HIUs can increase time when it takes to get to the domestic hot water. Now, there's 2 types of HIUs that are available common in the market. We have what's called a mechanical HIU or an electronic HIU. So what we're trying to do is look for the fastest response times for the end users, and that tends to come from domestic hot water. We don't really notice when we turn the heating on how long it takes to raise get. We know that within 10 or 15 minutes, they're going to be hot. The room's going to start, the property is going to start to warm up. Domestic hot water, we turn it on, we want hot water there and then. If you're waiting for mechanical valves to operate, those can obviously have a lag because they are mechanical. So we have to bear that in mind. Then this puts more reliance on the HIU's preheat, but as we know, this wastes energy and can lead to greater system losses or corridor overheating. We'll look at some preheat stuff later on. The control valves in certain HIUs, including ours, are controlled electronically, and this allows their position to be changed based on multiple different parameters rather than just one. So if we see a demand for hot water on electronic HIUs, the valve will open in what we call a boost function. So it will open as fast as it can to its full opening. The plate will get hot and it will start to modulate itself down to regulate the rest of the flow going through this. So it's just a bit of comparison. We'll look at mechanical versus electronic. There's probably pros and cons to both, but the response times that we can get through electronic HIUs tend to be a lot better and a lot quicker and better for the end users, and less reliant on the preheat or the keep warm function as well. And in a similar way to the primary pipework, the volume of water in the domestic hot water pipework within the apartment affects the response time of the taps. The cool water will need to be purged before the hot water reaches the outlet. So the more run of pipe work we've got away from a heat source, the more it's going to take, or the more time it's going to take to purge through to get hot water to the outlet. So you have to be really, really, conscious of how we design the apartments. The damage to this pipework is therefore needs to be minimised, and the vast majority of apartments of 15 mil of hot water should be fine. So you don't really need to run 22 mil or 28 mil pipe work around. 15 mil will suffice, and the smaller the pipe work, the quicker the diameter, the quicker you're going to purge the hot water through and the cold water out of the system. Alternatively, a manifold domestic hot water distribution system using a microbore pipework for the outlets may reduce domestic hot water times even further. So people think that by putting smaller pipework in, we're adding restrictions into the system, and to a degree we are, but we're also increasing the velocity as well, so the water will move through them a lot quicker. So when we look at some design considerations of heat networks, we have to prioritise what's good and what's high importance, what's low importance. And we've tried to sort of put a bit of a table together here which show which is which. So first of all, your network flow temperatures, what sort of network are you going to run at? What is going to be your primary flow, primary return temperatures? The apartment demand calculations, that's heating and domestic hot water. HIUs, underfloor or panel radiators, maximising the approach temperatures. What domestic hot water output do you actually need? What domestic hot water temperature do you actually need? Do you need 50 degrees? Do you need 55 degrees? We have to be real here. We're trying to save energy. We're trying to be as efficient as we can. So, we've got to look at that comfort versus efficiency. So we have to work it out from there. The heat interface with the HIU selection. Have you got the right HIU for your build? Delta T calculations are important. So you've got to work out, design your system based on your delta T's. Good design then will allow you to do that. Network size, and that comes from pipework, pumps, thermal stores, energy stores, energy source or sources. We looked at that before, how we size the energy source. Low temperature hot water, the pipework layouts. Is it the optimal layout? We'll look at pipework layouts shortly to make sure we're optimizing how we do that. Keep warm strategy, how is it being used? It's really, really important. Again, it's something we'll look at as we go through. Bypass strategy, again, really important thing to think about. A bypass is essentially an open loop between the flow and the return. It's going to have a huge impact on the return temperatures. Weather compensation strategy, are you using that weather compensation? Billing, how are they going to bill? Is it heat meters? Is it credit billing? Is it pay as you go? All those things need to be considered. Remote commissioning monitoring, we're seeing more and more of this now in the networks, especially with electronic HIUs, where people want to be able to dial in remotely via an M-bus or a Modbus system and start talking to the HIU and work it both ways. And then also on top of that, ongoing monitoring, adjustment, energy centre, HIUs, etc. for optimization. So, we live in a world now where a man in a van is a dying trade, and someone's sitting behind a desk and sort of dialing and doing things electronically to try and save time, and cost is becoming more and more efficient. So we have to look at that when it comes to designing the HIUs and your selection as well. Is it your high importance for you? But this is the sort of list that we've put together to try and demonstrate what we believe to be high importance over anything else. So, again, we go back to where we are. High pump speeds, minimum turn down. We spoke about this before. We're trying to slow the pumps down. We only want the pumps to pump when we need water. We want them to act on demand. We don't want to sit there as a slave run 100%, just pushing water through the system all the time. It's not what we need. We want to control them properly. Keep bypasses to a minimum. Refer back to CP1. What does it state? A bypass is just an open loop between a flow and a return. We need to keep them as small as possible. If you are using bypasses, have they been commissioned, or are they being commissioned? How are the network bypasses controlled? Are you using thermal control? Are you using differential bypasses? I've seen them as crude as people using a ball valve and cracking it half open, stuff like that. So you've got to make sure your bypass control is correct. The HIU keep warm is a bypass. If you're trying to keep your HIU warm at any one time or keep that domestic hot water plate, it will act as a bypass. It's an open loop between the flow and the return. Check your HIU keep warm flow rates. Is it a trickle bypass? Is it temperature controlled? Is it programmable? Something again we'll look at as we go through. Check the HIU keep warm method. Again, we said, is it programmable, trickle, or temperature controlled? Check the differential pressure capability of the HIU. Really, really important. There's a minimum and maximum differential pressure from the primary network HIU can work to. Make sure you're operating within those. Ensure that HIU does not have a DP bypass. Is that what we're looking for? Or all of the flushing bypasses closed? A key thing to network efficiency is flushing bypasses. They're a key part or a strategic part in the HIU itself, because we need to be able to flush through them. But if they're left open, they will starve the differential pressure from the HIU. Your efficiency will drop. You won't get any hot water out of the tap, but you will get really high return temperatures. So make sure they're all closed. A communal heating area. Again, we are looking for optimum temperature within a dwelling. If we're running communal heating those, how is it controlled? Is there any control? Is that just become an open loop? You know, you hope heating areas for the sake of heating them, something that must be another consideration when it comes to heat networks. Also, small approach temperatures, well, you know, we're starting to reduce the temperatures. We're seeing more and more now a want and a need to reduce the flow temperatures from 70 degrees all the way down to sort of 50, 55 degrees now. So, you know, optimizing those approach temperatures is also key. So we're looking at sort of bypasses and networks now, and where we are. So network bypasses, method of control. We spoke about different ways. Are you using differential pressure control? Are you using temperature control? Are you using, you know, a very crude way of just cracking open a bore valve? There's so many different ways that we can control bypasses in the network. So it's really important that you understand what's best suited for network, but also keep them to a minimum. As we said before, the bypass is just an open loop between the flow and the return, so it's always going to have a real issue on the network performance. And note that high differential pressure could affect the performance of some components within HIUs. And it's like the primary differential pressure could rise above 80 kPa. So look for what the maximum differential pressure rating is of a HIU to ensure that you don't get any issues, you know, in the cycle or the life of it. So if we're going to start lowering return temperatures or lowering the return temperature even further, we need to look at how we can utilize it. How can we get the most efficiency from our heat network? First of all, utilize underfloor heating where possible. If we look at a system itself, if we imagine, you know, the surface area of a floor with underfloor heating, that is far greater than any panel radiator you're ever going to get on the wall. So that means that the heat transfer or the energy transfer you can take out of the system is far greater. You're circulating at a lower temperature, but you're also extracting more energy because you've got a greater surface area. If you are going to remain with radiators, increase the radiator surface area. I'm sure that we've all sort of read in the news about installing heat pumps that run at lower temperatures, etc. And one of the things I always say when you install a heat pump is that you have to increase your radiator panel your sort of surface area. It's no different for this. If you want to get more efficient, the bigger the surface area, the better it's going to be. Things like fan-assisted radiators, if you are taking heat out, blow that heat around, use it as much as you can, extract it from the radiator, push it into the room and make sure the room's getting as heat as best they can. Diagonal cross flow through radiators, we are very good in our country of just putting the radiators at the bottom. But, you know, if you want to get true, real sort of efficiency through it, you should have a flow through at the top and then you return at the bottom so you can pour the water all the way through the radiator as best we can. Put your TIV heads on the horizontal. The valve will operate more efficiently when you do this. Learn the domestic hot water set point temperature. You know, do you need 55 degrees? Can you drop it down to 50 degrees? You know, thinking about all things like this is one of those, and don't always look at increasing the approach temperatures to try and increase this. It's a no-no. Now, there are things that we can do within a network to increase the efficiency of it. So, learn to, you know, what can we actually achieve? Now, let's look at some seasonal averages. We can see here now we've got spring, summer, autumn, and winter. We've got flow temperatures of 58, 55, 57, and 59. And we can see there the blue band is the delta. So we've got 33 degree delta, 28, 30, 33. But we've got return temperature here of 25, 27, 27, 26. So we can maintain a fairly steady, strong delta across the seasonal average. And these are seasonal averages and our return temperatures. You're going to see different fluctuations, different times of year because there's different demands on the building, different heat loads. The way that we use the heat is slightly different. So, you know, across the season, across a year, average-wise, you know, we can achieve those nice deltas as best we can. Now, we've been talking about network losses, about the way that we lay out our pipe work, etc. This is now really key now to where we start looking. This is information that we look at things like CP1, where we start to really look at optimal performance. So, the low temperature hot water system, your bypass control, the method, the number, you know, the keep warm functions, a pump turn down, approach temperatures. So if we look at pipe work layouts now, there's two diagrams here, one on the left and one on the right. What we class on the left hand side is probably the most inefficient way that we can do it. And the reason for that is we've got one riser, which is sitting on the end of the building. That hot water riser is rising at the end of the building. We've then got very long lateral runs, which go all the way down corridors, all the way to the very end, where we then feed into the apartment block to feed into the HIU, or the heat interface unit. Now, this is where we start to get overheating in things like corridors, network losses, you know, because we're losing so much temperature as we go down that lateral, and that long length of pipework is quite long. We're going to start to have more reliance on things like preheat because of the length of that pipework. If that pipework starts to cool down, it's going to take more time for the heat to heat the plate heat exchanger, and in turn for the HIU start producing domestic hot water. So look at an optimal layout. We would split that. We divide the system into 2 risers. So we'd have 1 riser going up one side of the building and 1 for another. And we keep those short runs in the laterals as short as we can. So as we come off the riser, we just share off a short amount of pipe work into each individual apartment. So we look at the primary, the best way of doing it, the most efficient way of doing it would be the one on the right-hand side. Something needs to be considered at the design outlet, because you need to design into the system that you're going to have 2 risers, but in the long run the efficiency in network is going to be far better because you just reduce the amount of pipe work. As I said before, a hot pipe is essentially a radiator traveling around a building. Yes, we can insulate them as best we can, but we're still going to suffer heat losses through the system. Now if we move into the actual dwelling itself, we're now trying to look at how we can do this even better. So overheating of corridors, we spoke about that. The amount of times I've certainly been to sites and I walk into a corridor and the heating there is huge. Even though they've got any radiators, but it's just all coming from the pipe work. It's just running really inefficiently. We're oversizing the lateral pipe work, which is giving greater heat losses. Are we achieving the flow rates or the velocity through the pipe work that we need? We're going to have a low delta T. Insufficient lagging, is BS 5970 is not good enough. We need to look at it. We need to move forward. Network bypassing, again, we said, network bypassing is an open loop. The temperature, or sorry, the low temperature hot water pipe work lagging is the key to optimally get that right. Valve and flange lagging, it's all great if we start to flag lag valves, pipe work, but we've got to remember there's valves and there's flanges in there as well. They also need lagging. Low conductivity brackets, so the bracket doesn't work as a heat emitter. We keep as much heat as we can, but also communal heating areas, we've got to keep those to a minimum and try and do it as best we can when it comes to the layout. So if we look at some layouts of actual sort of plan views into apartment blocks now, so the top one that we can see there would be classed as a poor layout. Now the reason for that is we've got 1 central riser. We've then got long pipe work runs within the corridors themselves, but also the HIUs are situated quite far away from where the pipework enters the building. So you can see the red dotted lines inside the building. That denotes the pipework within the building itself. So what that means is that obviously there's more and more pipework for it to cool down. It's going to take longer response times for the water to come through. You're going to be a lot more reliant on preheat. If we look at a better layout, again, we can see we've still got that 1 central riser, but we've kept the HIUs as close to where the pipework comes into the system as possible. That then means there's less distance for the hot water to travel, less distance for it to cool down. So the efficiency goes in. You're going to be less reliant on things like preheat. But we looked at the best layout, the optimal layout will be the one on the right-hand side. We can see we've got 2 central risers. We've got very, very minimal amount of pipe work into the corridor space and very minimal pipe work running inside the apartments, because the HIUs are as close as they can be to things. So we're looking there, they're going to be very, very small demand or reliance on things like preheat. So when we look at optimal layouts, the one on the right hand side should be what we're looking to achieve when we're moving forward with design. So we spoke about some of the issues with networks. Lack of or fluctuating domestic hot water temperatures is #1 cause of complaint. People don't realise if their heating is 3 or 4 or 5 degrees low, but they certainly do if their hot water is. It can down to be a couple of things. The key thing or the optimum thing, the one that we always see the most, is pump control. Is delivering the energy we need to the most distant HIU. That's why it's key that pumps are controlled correctly using what we call an index sensor. So the most remote part of the system, set your index sensor there, set it to the minimum you need. So if a HIU needs a minimum of 50 kPa, we could set that index sensor to 60 kPa, so we know we're delivering more than enough differential pressure to the most remote HIU. As we then come close to the energy center, we know we're going to have an abundance of energy to work there through. So pump control is key. Differential pressure, determined units that goes with the pump control. Imagine as pushing energy through. The more hot water and more energy we can push through, the more efficient we will be. Lack of network circulation, so the water is very lazy. It will go wherever it wants. So we need to force it to go to the most distant parts. Also use things like thermostatic mixing valves. There can be a conflict between the HIU and the TMVs. If you've got your domestic hot water set to 50, you've got a TMV set to 42, you haven't got the delta, there's going to be a conflict between the two. So always remember, when we're doing that, you may not necessarily need a TMV or another way to blend that hot water down to a safe usable temperature. So always remember, index your pumps, make sure you've got your index sensor at the right point, you're delivering the correct KPI to where you need it to be. It's always key in remembering that. So as we look at the heating side of things, low heating kilowatt loads. So, we're not using the energy that we need, increases the delta T's of the system. So results that is low flow rates, difficult to balance the heat emitters because we're not getting the flow rate through there. The ways that we can overcome this is using things like presettable or pressure independent TRVs or dynamically controlled. What that means is that we can preset the flow rate through every single radiator to ensure that's going to go there. As we've said before, water is very lazy by its nature. It will go through the closest radiators first, and the most distant ones in an apartment will suffer with flow issues. But if we can set the flow rate to each individual one, presettable is great, because we guarantee the flow rate through each individual one. It's still a manual way of doing it. We can still imbalance the system should something come along. Use something like a dynamically controlled or pressure independent thermostatic radiator valve. That then every single radiator becomes an independent zone. So no matter what you do to the system, you're still delivering the right flow rate and the right temperature at any one time. So that's something to consider as well. But also we have tenant-driven issues. Those be, the people that are inside the flats themselves. They tamper with radiator valves. We've all done it. You turn the turn the heating up, turn it down, turn a radiator off, take it off the wall, whatever it may be. But it always has an impact on the system. Installing things like radiator covers, they may look lovely, they may look nice and cover this horrible big white piece of steel on the wall, but they do have an impact on the heat that can be taken away from the radiators. Putting a couch against the radiator, I'm not going to say that I've never done that in my house, but someone putting a sofa in front of the radiator is a big no-no. Drying their washing, again, common things that I'm sure that we've all done at some point. We stick some wash onto the radiator. It all adds to the inefficiency of how they work. Return temperature limitation into the HIU. So some HIUs have what we call a return temperature limitation. We talk about trying to deliver a set return temperature that can be controlled by the HIU. You can set your return temperature and it will make sure that it achieves that. However, there will be some implications on how it can deliver the hot water into it. So, you can't sort of have your cake and eat it when it comes to things like return temperature limitation. So we look at things like space heating startup now, and this is, the reason why we say this delivers an issue to the network is because of the way it forms. So we designed a load for 3 kilowatts or, a 3 kilowatt apartment load. On initial startup, this can pull up to 6, 7, or even 8 kilowatts for the first 10 minutes. So because we're trying to pull that heat through as quick as we can to satisfy a heat demand. So if every single apartment was to turn their heats on at the same time, you're pulling, 3 or 4 times more the design side of the system, what it could be on the heating side. That's something to consider. Difficulties in commissioning. Apartments have to be brought online in phases. So what I mean by that is when we're doing it, don't just turn everything on at once. We have to do it in a phase process so the network can settle down and work as it needs to be. If a high number of apartments all go into heating mode at the same time, the network can fail, and this is more likely in periods of domestic hot water use. We spoke before, the load on the network is far greater when we're using domestic hot water because the energy transfer is so much greater. So we have to remember that when we are using it, a lot of people using heating at any one time, that by using that at the time of heating and hot water, we can have issues. It becomes more likely as the network size is optimized, becomes more likely when overheating is addressed. Difficult to counter, so oversized thermal stores, oversized boilers, primary flow rate limitation, all these sort of things that need to be looked at to ensure you've got optimization when it comes to a network not falling over under certain loads and certain demands. So we talk about approach temperatures. When we talk about approach temperatures, we're talking about the deliverance temperatures to the HIU. So the approach temperature, difference between primary flow temperature and secondary flow temperature, domestic hot water and heating. We need to maintain reasonable approach temperatures. The smaller the approach temperature, the higher the primary flow rate and the higher the network return temperature on a given output. So we've got a couple of examples here where we can see we've changed some parameters. So we've got 70-degree flows that come into the HIU. On the first one, the heating, we've got a 65-degree flow, and on the right-hand side, we've got a 60-degree flow. But we can see the impacts that we have on each side. So with the 65-degree flow, we're looking at 49, so nearly 50-degree delta. If you drop it down to 60, we're looking at a 41-degree return temperature as well. So we can see there, by getting the systems balanced, by changing the temperatures, the parameters, how that can have an impact on that. And this is a simulation tool that we run through plate heat exchangers to give an indication as to how the HIU is going to perform at any one time. If we move on to domestic hot water approaches, so we can see here again, we've got different temperatures approached onto the network. So we've got flow temperatures of 60 degrees, we've then got 50, 55 and a 50-degree temperatures, and we can see how that impacts, on the return temperatures. So at 55 degrees, return temperature is 22 degrees. On a 50-degree flow, we're looking at 16 degrees. Now, On a simulation tool, if it's impossible, if the HIU can't perform to what you achieve to do, we can't give you a calculation. So it's really important that we get the correct information when it comes to sizing it, or trying to run some simulations to make sure you're getting what you can. And all that will identify your flow rates through your primaries, your flow rate through your hot water as well for your outlet. So you get 15 litres a minute, 18 litres a minute, whatever it may be. We can optimise that and we can tailor that to how it needs to suit your system essentially. So, working with lower primary flow temperatures, 4th generation and 5th generation networks. There's a lot of talk about this. I'm not going to spend a huge amount of time on it because I think it's probably something that needs its own time to dedicate to talk about. But we can look at what we're going to start to look at when we're working with lower temperature networks. And HIU's maximum output will depend on the energy it receives. The lower the flow temperature, the HIU will either lower its output or take higher primary flow rates. It's essential to maintain a reasonable approach temperature. With a 60-degree primary flow, then you cannot have 60 or 70 kilowatts of domestic hot water. And with a 60-degree primary flow, you cannot have domestic hot water at 60 degrees. So you can't have your cake and eat it, is what we're trying to say here. So if you are going to start reducing flow temperatures into the HIU, it's going to have a detrimental effect on what can come out of it. We have got the technology nowadays. If you want to deliver, say, for instance, 55 degrees primary flow as an energy source into a HIU, we can probably give you 50, 51, maybe 52 degrees out, depending on what the demand is, by using bigger, longer plate heat exchangers. But again, like we say, you can't have your cake and eat it. You can't just keep dropping temperatures and expect the HIU to function, without any issues, because it will do. So that's what we sort of look at when it comes to lower flow temperatures. But I think this is something that needs to be discussed, in its own training session, on its own. We spoke a lot about keep warm. Is it needed? It really is a minefield when it comes to keep warm. We look at trickle bypasses or trickle keep warm functions. Is 100 litres an hour a trickle? I don't know. It's for you to decide. I don't think I'd want 100 litres an hour dripping onto my carpet at home. So it's probably a substantial amount of water. Why do we need keep warm? Well, what is keep warm? If anybody's not sure on the call what keep warm is, basically what we're trying to do is keep the plate heat exchange, the domestic hot water, hot at all times. So when you turn the tap on, you're going to get almost instantaneous hot water. But that does have an effect, as we say, because it comes an open bypass. But why do we need it? Slow-acting HIUs and control valves, long and oversized lateral pipework. We've discussed all this previously through the presentation. Long and oversized domestic hot water pipework. So the pipework sizing is key. The more issues you have with the initial design stage, the install stage, the more issues you'll have on efficiencies when moving forward. The downsides of using things like keep warm: increased energy usage. You have to pay for the fact you're keeping your plate heat exchanger warm. Decreasing network delta T's. Again, it does become an open bypass, so the delta T on your network is going to massively reduce. Increased network losses because we're constantly sending hot water around the system. It's going to be a higher bill for the tenants. Can you achieve your 50% losses according to CP1 if you're using certain keep warm functions? And should you rely on something that a tenant owns with restricted access to make the system work? Essentially what you're doing with keep warm is overcoming design issues at the initial stage. You're expecting the tenant to then pay for that. So something to consider, when it comes to the keep warm. But if you are going to use it, what's the best way to go about it? The historical lack of HIU standards allows some manufacturers for HIUs with very poorly performing keep warm functions. And CIBSE CP1, which is the code of practice for district heating heat networks, always states to keep bypasses to a minimum. So if we look at poor, better, best, a poor way of doing it will be a trickle bypass. That's a continuous bypass of primary water through the domestic plate heat exchanger. No temperature or time control, extremely wasteful, high return temperature and small delta T. So that's where we're looking at like a real poor, if you've just got an open loop between the two. A better way of doing it will be temperature control. And these bypasses are primary water through the domestic plate heat exchanger. Once the plate the plate heat exchanger temperature drops below the setback temperature, it can give reasonable results, but no control over the primary return temperature can be switched off when it's not required. So what we're saying here is we've got thermostat control. As the temperature gets warm enough, it will start to close itself down, but open, but it can't be turned on or off. It's just a different way of doing it. Now, the best way to do it would be a configured way of doing it. It is obviously stated in CP1. And this utilises the benefits of a setback temperature control, but can also ensure specific return temperatures are not exceeded. Can also be switched off, on, or configured in a similar way to setting your heating time, so that keep warm is inactive while you're asleep or at work, for example, and the keep warm function can be remotely configured individually or globally. So what I mean by that is you can set your keep warm to come on exactly the same as you would with your heating and hot water on a standard boiler. If you know you're going to have a shower at 7 o'clock every morning, you set your keep warm to come on at 6 o'clock. You plate heat exchanger with nice and hot when you want to have a shower. You then switch it back off at 7:30. You're only using it for that hour and a half. You're only paying for that. It's not going to be a 24-hour service that you're going to be paying for when you're not necessarily going to be using it. So something to consider when you're looking at specifying how to use the keep warm functions. Something we can look at now about the volume or the VWAT. So we're looking now at the return temperatures over different ways of doing it. So when we've got 24-hour keep warm, we can see there that if we keep her on the total volume, which is the yellow block, if we have a 24-hour keep warm, we can see the volume of water is quite large in meters cubed. If we then reduce that down to 8 hours keep warm, it reduces it down again. 6 hours of keep warm again, and 4 hours lowers it even more. So if you can use it configurable, if you can use it in a way that means that you can program it just to come on for an hour a day, that number is going to come down even more. So the efficiency of your network is going to increase. So if you are going to use things like keep warm functions, make sure you're using the correct type of design for the system that you're working on. So HIUs, how can they assist or hinder efficiency? Again, it is a bit of a Wild West saloon. It has been for a time, but it is getting better. There's lots of industry standards now that come into place to make sure that we get this. So the good things: thermostatic controlled and configurable preheats. We've just spoken about that. Long plate heat exchangers, which increase the delta T, so that we use as much energy as we can from the system. Fast acting motor driven control valves, because it's electronic, it can open up as quick as it can. We can get the hot water delivered as quick as we can. High differential pressure capability. Gone are the days where a maximum of 130 kPa could go through a heat, for a HIU. We can now go up to like in excess of 600 kPa going through the HIUs. Return temperature limitation, so we can limit the return temperature. Again, it will have an effect on the performance of the HIU, but it's something to protect the system. Primary flow limitation, so we can balance that primary network because we know exactly what flow rate is going to come through the primary network. Clamshell insulation, it's something that's been driven now by some of the test standards to make sure that the HIUs are installed as best, or insulated, as best as they can be, to minimise the heat losses and increase the efficiency. Some of the bad things, so it's wasteful permanent preheat bypass is a trickle, it can be 100 litres an hour. Short plate heat exchange, so the energy transfer is a lot less. On-off control valves, they're on or off, there's no modulation. Slow acting control valves, generally when they're mechanical. Integral thermostatic mixing valves, not electronic. Low differential pressure capability, and there are some that are still uninsulated. So, we can massively help the networks, but we can also hinder it if it's not a good design as well. So something to consider alongside there. So just to wrap up, as a summary, take a holistic approach. Don't oversize. We've spoken at length about everything that can be oversized. Accurately calculate domestic hot water loads. Ensure accurate balancing for the space heating, using things like presettable, dynamic controlled radiator valves. Optimizing low temperature hot water layouts, make sure that they are as good as they can be. Increase the velocity in the lateral pipework, reduce the bore of the pipework, increase that pascals per meter to make sure we're getting that good effect. Utilize 15 mm domestic hot water pipework for the vast majority of apartments. Locate the HIUs close to the corridor as possible, next to the majority of the outlets, so reduce the amount of pipework we've got running through. Minimise the number of bypasses. They are just open therm to a system. We need to make sure we keep away from that. Correctly control any system bypasses. You're going to have some in there, but just make sure they're correctly controlled, but also ensure that they control the pump by its index. Again, it's something which is key, is controlling the pump by its index. And finally, heat meters. Every flat or every HIU should have a heat meter. You can learn a lot from what's going on. So you can use the apartment energy meter during the commissioning. Is there a primary flow rate through the HIU when there shouldn't be? Can you do some diagnostics from that? What is the primary flow temperature of the HIU? Is it stable? Is the primary flow temperature below the secondary set point temperatures? So if you've got a primary flow coming in at 55 degrees and you've got hot water set to 60, you're not going to get 60 degrees. I can tell you that for free. And what is actual delta T that's been achieved on the HIU? You can read your delta T through the heat meter, both in heating and a hot water mode. What's the keep warm flow rate? So if you are using the keep warm function, you can see what the flow rate is through there. What is the keep warm delta T? What impact is it having on the network? And then Modbus take things even further. So, just by simple, modest heat meters installed in the HIU, we can tell a lot from that when we're doing site visits and obviously speaking to customers over the phone. And that is the end of my presentation. So I thank you all for taking the time to listen. I'm guessing there's probably some more questions. Yes, okay. I'll have to go back to where I was before. Okay, so if we work for the energy sensor supply and thought, I've already answered that one. What are the primary delta T would you consider for primary heating? Domestic and domestic. Did I answer that one before? I say delta T is as wide as you can. You know, it's all about how you balance your system, but I think we answered that. But there's some stuff. We have a network guide which can give you some things to consider and some considerations to take when it comes to things like that. What are the commissioning parameters for HIUs? Meaning what flow rate and pressure should it be tested to? Okay, so this is always a real grey area when it comes to commissioning HIUs. The HIU is interface between the primary network and the tenant. What we tend to do on the HIU is set the parameters what is needed for comfort. So we'd set the flow temperatures for the heating, we set the flow temperatures for the domestic hot water. All we have to ensure to achieve that is that we're getting the correct differential pressure, or the correct energy coming from the primary network. So if you've got a HIU or a primary system which is designed correctly, we're achieving the minimum differential pressure of the HIU, then all that should fall hand in hand. They're actually quite simple to use. We have a way here of what we call pre-configuration of of HIUs. So we can almost pre-commission it before it comes to site. We can get all the parameters. We can load them into the HIU as soon as you put into your system, providing you've got your minimal, the minimum differential pressure of the HIU, then that will work. So hopefully that's covered off that one. Where does exactly the DPS sensor sit on the riser, or does it blow DPS? Different. Is that the difference? Is that? Sorry, on that one. Just going back up to the question. I'm just trying to understand what it is exactly, which sensor is referring to. Are you referring to the pump sensor where we'd read for the pump? If you could just clarify that one, I'll go back and answer that one shortly. Thermal science is based on 10 minutes of peak demand. Would be just enough. Oh, hang on. Would be just enough. Would the primary source heat kilowatt matter for reheating? Of course, when it comes to pump sensor, that's one back. Yes, so I mean, what we're looking for is worst case. Obviously, we've got to look at the regeneration or the restoring of the thermal store as well. That 10 minutes is based off a code of practice. That's what the recommendation is. Obviously, everybody will have their own sort of parameters, what they work to. But I think as a rule of thumb, that's what they sort of say is 10 minutes of peak demand. That's a lot of water. If you've got a diversified load, that could be thousands of litres, if you know what I mean. So yeah. But would the primary source heat kilowatt matter for read? And obviously, the higher the heat, the higher the kilowatt rating for the primary, the quicker it, of course, will reheat. So there are ways of achieving that. So yeah, I hope that's covered that one up. Yes, pump sensor. So no, it's got to be at the most distant point. Obviously, if you've got an end of run bypass up there, you want it before that, because you want to make sure we're achieving it before we get to the differential pressure control, whatever it may be. But yeah, pump sensor should always be set at the furthest point in the pipework to ensure that the pump knows exactly what's going on within the system. But again, if you look at the, I think my colleague has just shared there a guide to networks and stuff, what we have. So any information that you may need can also be found in there. It's good for guidance. Also, CP1 is another one that we've mentioned as well. So there's plenty of information out there for everyone to read should they come to need any more information than what we've shared today. So I can just see that somebody else is typing, so I'll wait for it's going. At the furthest point or the index run. So, well, okay. So it depends on looking at it. I can go back to the diagram now. But we want to put the most remote part of the system where we're going to require differential pressure. If I can try and go back, sorry for anybody who might be bored of this, but I'm just trying and show it on the diagram if I can. When we talk about pump sensors. My apologies for anybody who's not concerned. So we can see here on the diagram, which I've just seen, which has gone past. So I'll just catch them. Still going backwards now, not forwards. I clicked it too many times. Right, sorry, apologies. I'll be with you in 2 seconds. Yeah, let's see. So you can see. Oh my God, I'm really sorry. I get there. Yeah, okay, so we can see here, this is the most remote part of the system. This is the furthest point. If we were to put an index sensor, I'm sorry, you can see my mouse, I'll put my mouse up here. So this is the most remote part of the system. Can you see my mouse on that screen? Yeah. So the index sensor we've put here, which is the most remote part, if we were to install it here, then there's obviously still a lot of pipe work to run up here to see what it can do. If we put it here, it's not the most remote part, because the water's lazy, it will circulate around here and not necessarily push itself up here. So we would always recommend it at the furthest point. Now, different pumps will work off different ways of sensoring. So you know, in an instance in this, I would always get clarification from the pump manufacturer or the booster set suppliers or whoever it is that doing the pumps to get where they would dim it. But it has to be at the most remote part of the system to ensure we get the right amount of differential pressure or energy to go through the HIU. So hope that one's cleared up. But in any case where there may be some questions, you know, always speak to the manufacturer and see how their equipment will work best with anything like that. So hope that's clear. Well, I take, you know, appreciate everybody for taking the time to listen today. I know it's been, you know, a fairly long one on this one, but it's always quite a you know, quite a long one to talk about. So my email address has just been shared by my colleagues. So if you do have any emails, please feel free to contact me directly, and I'll do my best I can to help you. And again, I thank everybody for the time. I appreciate it. Everyone's time is very precious. So thank you very much, and we hope to see you on another Altecnic CPD.